Hello and welcome. My name is Ian Fletcher. I am the Senior Product Manager for Temperature Resistant Coatings, and I shall be giving this presentation on maintenance solutions for CUI and cyclic temperatures, which will take around 30 minutes. This is the second of two presentations on this topic. In the first presentation, we discussed corrosion under insulation, its causes, implications, and challenges. I then went on to present a novel hot spread epoxy coating called Intertherm 2205. In this presentation, I will present two other important maintenance solutions for CUI and cyclic temperatures, namely Interbond 2340 UPC and Intertherm 751 CSA. Let's recap AkzoNobel's product offer for the CUI and cyclic temperature maintenance market. For planned maintenance shutdowns and regular maintenance for process piping and equipment operating below 230 Celsius, Interbond 2340 UPC should be used. For planned maintenance shutdowns and regular maintenance for process piping and equipment where operating temperatures are cyclic and are between 230 Celsius and 400 Celsius, Intertherm 751 CSA should be used. And for applications to hot process piping and equipment operating between 60 degrees Celsius and 230 degrees Celsius, Intertherm 2205 is the product of choice. This chart shows the operating temperature ranges for the three products. All three products can be used at cryogenic temperatures as well as temperature ranges from ambient to high temperature conditions. But when it comes to direct-to-hand prepared hot steel applications, Intertherm 2205 is by far the best choice. With hot steel applications from 60 to 205 degrees Celsius. The rest of this presentation will now focus on Interbond 2340 UPC and Intertherm 751 CSA. Let's start with Interbond 2340 UPC. Interbond 2340 UPC, where UPC stands for Universal Pipe Coating, is an alkylated amine epoxy technology, which is a next-generation epoxy phenolic, delivering low temperature cure and higher DFT tolerance compared to traditional epoxy phenolics. Interbond 2340 UPC is a user-friendly maintenance coating specifically designed for combating CUI that helps generate time and cost savings through fast, low-temperature drying and improved application tolerances. 2340 UPC has fast, low-temperature cure and is dry to overcoat in 14 hours at -5 degrees Celsius. It meets the ISO 12944 Part 9 performance criteria for an ambient cured coating. It has excellent tolerance to over-application, can be applied to hot steel up to 120 degrees Celsius, has high temperature resistance to 230 degrees Celsius, can be used at cryogenic temperatures down to -196 degrees Celsius, and can protect stainless steel against chloride-induced stress corrosion cracking. Okay, let's look at 2340 UPC's features in more detail, starting with its fast curing property. Typically, traditional epoxy phenolics will not cure below 10 degrees Celsius. Issues such as maintenance project delays can then happen when temperatures drop overnight or when maintenance needs to be carried out in the winter months. Conversely, 2340 UPC can be used down to -5 degrees Celsius, being hard dry in 10 hours at this temperature. As you can see in the table, 2340 UPC has faster hard dry times and has much lower overcoating times than traditional epoxy phenolics. This means that compared to traditional epoxy phenolics, Interbond 2340 UPC allows process piping and equipment to be re-insulated and put back into service up to 85% faster, greatly improving the productivity of maintenance teams. Let's now consider over-application tolerance. Again, if we look at traditional epoxy phenolics, we see that they tend to have poor application tolerance, and datasheets often state maximum scheme DFTs that must not be exceeded for fear of crack formation. Sometimes cracking is not seen after application and will only show itself once the coated steel is back in operation. If this coated steel is insulated, we will never know what is happening, and so the CUI risk now becomes very high indeed. As a way to demonstrate 2340 UPC's resistance to cracking due to over-application, a detailed test program was carried out by AkzoNobel. In this program, panels containing a weld are cured at ambient for 7 days and then subjected to 5 heat cycles. One cycle consists of 8 hours at the target temperature, followed by 16 hours cooling to room temperature. Panels are then assessed visually for cracking, blistering, and disbondment and graded. Green, no visible defects. Orange, cracking and defects observed around weld only. And red, cracking and defects observed across the face of the panel. Here we can see the performance of a so-called average performing epoxy phenolic. Heating to 120 degrees Celsius, we see good performance for schemes up to 2 times 175 microns. But then, after that, cracks around the weld start to appear. Heating to 150 degrees Celsius, we see a different picture. All schemes have cracked badly across the face of the panel except for one scheme at 2 times 100 microns, where it is likely that solvent entrapment is lower, and so the scheme becomes less stressed on heating when solvent is released. However, when panels are heated to 200 degrees Celsius, again we see that all panels have cracked badly, with this time cracks being just around the weld for the 2 times 100 micron scheme. Nonetheless, all panels have cracked and so failed the test. Overall, it is fair to say that this epoxy phenolic is very sensitive to over-application, and other than a narrow application thickness for optimum performance, it cracks badly in the test. Now if we look at a so-called well-formulated epoxy phenolic. Heating to 120 degrees Celsius, we see good performance for all schemes. Heating to 150 degrees Celsius, we see good performance up to 2 times 150 microns, but then cracks start to appear around the weld for higher DFT schemes. Now, if the panels are heated to 200 degrees Celsius, we see a mixed picture. Initially, there is cracking around the weld, but then we see good performance for 2 schemes. Again, likely because of lower solvent entrapment in each coat, but then cracking around the weld is seen for higher DFTs, with 2 times 250 microns scheme cracking badly. This epoxy phenolic has a slightly wider application thickness for optimum performance compared to the average performing epoxy phenolic, but as thicknesses and temperature are increased, we generally see cracking around the weld. This is 2340 UPC's performance in the same tests. Here you can see for all test temperatures and DFTs, there is no cracking whatsoever anywhere on the panels. Interbond 2340 UPC shows excellent tolerance to over-application. Another important consideration when comparing epoxy phenolics is heat resistance. In this study, 2340 UPC was compared against 6 other traditional epoxy phenolics currently in the market. All of them are typically specified for service up to at least 200 degrees Celsius. All schemes were applied at 2 times 125 microns and all cured at 20 degrees Celsius for a minimum of 7 days before testing. After 6 months exposure to 205 degrees Celsius, we see differences in performance. One coating showed significant cracking after just 6 weeks, another significant cracking after 12 weeks, and one some minor cracking after 3 weeks. 2340 UPC and 3 other coatings performed excellently. Let's now review 2340 UPC's enhanced corrosion protection feature. In this study, 2340 UPC was compared against the same 6 other traditional epoxy phenolics currently in the market. As before, all schemes were applied at 2 times 125 microns and all cured at 20 degrees Celsius for a minimum of 7 days before testing. All panels were exposed to 25 cycles of the ISO 12994 Part 9 test standard as used to qualify coating schemes for offshore CX environments. As you can see, only 2340 UPC performed well in terms of rust creep and no corrosion spots away from the scribe. One coating system showed particularly bad corrosion across the face of the panel. Several coating schemes failed the test with greater than 8 mm corrosion creep, and 2 were close to failing. Okay, let's now look at corrosion under insulation. You will recall the Houston pipe test from part 1, so I won't go into the detail again. The test was configured to test the coatings up to approximately 400 degrees Celsius to clearly show the point of failure. Here you can see the results from the 2 pipe tests. On the right is a traditional epoxy phenolic, and on the left 2340 UPC. The results show that both products show very good performance up to around 240 degrees Celsius and so are suitable for CUI protection. 2340 UPC has a slightly higher temperature tolerance, which is particularly useful for temperature spikes experienced during steam outs. So to summarize, traditional epoxy phenolic solutions do not cure below 0 degrees Celsius, and in most cases not below 10 degrees Celsius. Traditional solutions are sensitive to over-application and can crack in service, leading to performance and cost issues later on. Interbond 2340 UPC is fast curing, meaning it can be re-insulated up to 85% faster than traditional epoxy phenolics at 20 degrees Celsius. It can be applied down to -5 degrees Celsius, extending the maintenance window, has up to double the DFT over-application tolerance of other epoxy phenolics, has excellent corrosion resistance, allowing a single scheme to be used from -196 degrees Celsius to 230 degrees Celsius, and so reducing system complexity, and can be applied to hot steel up to 120 degrees Celsius. Let's now turn to Intertherm 751 CSA. Intertherm 751 CSA is a heat-resistant cold spray aluminium, an inorganic copolymer technology providing corrosion protection to steel in both atmospheric service and under insulation operating in thermal cyclical conditions. Intertherm 751 CSA is a user-friendly maintenance coating specifically designed for combating CUI in cyclic temperature conditions in the cryogenic to 400 degrees Celsius temperature range. Intertherm 751 CSA is a titanium-modified inorganic copolymer, cold spray aluminium, provides excellent CUI protection to carbon steel undergoing temperature cycling, has a proven track record dating back to 2005, has excellent resistance to thermal shock, can be used on SA2.5, SP11, SP3, ST2, UHP, WJ surface pretreatments, can be used to repair TSA field joints, can be applied on hot steel to 150 degrees Celsius, can be used at cryogenic temperatures down to -196 degrees Celsius, can protect stainless steel against chloride-induced stress corrosion cracking, can be airless spray, air spray, brush or roller applied, and can be applied at either 1 times 175 to 200 microns or 2 times 100 micron schemes. Let's now look at 751 CSA's key feature, temperature resistance. A key reason for determining the temperature resistance of generic coatings is bond strength. The best organic high heat coatings based on epoxy amine chemistry typically break down at temperatures above 230 degrees Celsius, whereas inorganic coatings have temperature resistance well in excess of 230 C, where some ceramic coatings can have a temperature resistance approaching 1000 degrees Celsius. 751 CSA is an inorganic coating that uses silicon-oxygen bonding to form its coating network. Silicon-oxygen bonds are much stronger than carbon-carbon bonds, and so 751 CSA has excellent temperature resistance up to 400 degrees Celsius. A word about more traditional solutions. Inorganic zinc silicates are indeed temperature resistant to 400 degrees Celsius, but they are not suitable under insulation as per the NACE SP0198 standard, and they are difficult to apply, requiring adequate temperature and humidity to fully cure. Aluminium silicones are temperature resistant to 540 degrees Celsius, but don't provide corrosion resistance under insulation, particularly in the CUI zone, and tend to fail under cyclic conditions. They also need to be applied in multiple coats of 25 microns each, which is time-consuming for applicators. Cyclic temperatures can give rise to different environments. In thermal cyclic operating conditions, for corrosion to occur, 3 key elements must be present, i.e. steel, water, and oxygen. Even without water, metals are still subject to corrosion, so-called dry thermal scaling. And then there is rapid cooling, which leads to condensation and subsequent corrosion problems during the operation cycle and shutdown. Many coatings work effectively at continuous high temperature, i.e. thin film high heat silicones. However, these types of thin film coatings, 50 microns, have very little corrosion resistance and so perform poorly in temperature cycles that enter the CUI zone. Intertherm 751 CSA has been specifically formulated to withstand the extreme effects of temperature cycling. Extensive track record and laboratory performance testing has demonstrated its ability to withstand elevated temperature exposure while still providing long-term corrosion protection. Particular applications where temperature cycling is prevalent are heat exchangers, stacks, and gas dryers. "751 CSA was born from the extensive screening testing carried out using the CUI cyclic corrosion pipe test, now known as the Houston pipe test. It is also now an optional extra test in the ISO 19277 test standard. The test simulates aggressive temperature cycles by using a series of heating and cooling steps. And to make the test even more aggressive, calcium silicate insulation was selected to maintain a high level of water saturation around the test pipe. Over 300 pipes have been put through the test, and here you can see how it easily differentiates between generic coating technologies. The epoxy phenolic is starting to degrade around 230 degrees Celsius, and the epoxy around 120 to 150 degrees Celsius. The zinc silicate shows corrosion along the length of the pipe, whereas 751 CSA shows very good performance across the temperature range. Note the left end of the pipe is the end in contact with the hot plate and is breaking down because it cannot be protected properly and so is discarded when carrying out coating performance assessments. 751 CSA was benchmarked in the Houston pipe test against two other products, A and B. Both are available on the market and both claim high temperature resistance to 650 degrees Celsius. Both are MIO containing coatings. Let's take a more detailed look at performance. In the CUI temperature range, 751 CSA showed no coating breakdown, and there was also no coating breakdown up to 450 degrees Celsius. Here is a closer look at the coating surface at 235 degrees Celsius and in the range 275 to 300 degrees Celsius. Both photos show no evidence of coating breakdown. When we look at product A, we see coating breakdown below 150 degrees Celsius and extensively in the region up to 450 degrees Celsius. Here we see the extensive coating breakdown at 235 degrees Celsius and in the range 275 to 300 degrees Celsius. Product B also shows some coating breakdown at 150 degrees Celsius and extensively in the region up to 450 degrees Celsius. And here is a close-up at 235 degrees Celsius and 275 to 300 degrees Celsius, showing extensive coating breakdown and corrosion. .751 CSA can also be used for TSA repairs. In this study, a TSA coated pipe was repaired with a brushed-on patch of 751 CSA. The pipe was then put through the Houston pipe test. In these photos, you can see that there was no evidence of coating breakdown, demonstrating 751 CSA's ability to repair damaged TSA. And here is a test showing 751 CSA's use as a field joint coating on TSA coated pipes. The field joint was prepared to SP11 with a power tool such as an MBX bristle blaster, and then the 751 CSA was brush applied. After two 8-hour cycles at 400 degrees Celsius, there was no cracking or blistering of 751 CSA observed. So to summarize, traditional solutions such as inorganic zincs and modified silicones do not perform well at both high temperatures and in the CUI temperature range. MIO-filled high heat coatings have been shown not to perform well in aggressive cyclic testing. Intertherm 751 CSA has a track record dating back to 2005, provides excellent CUI protection to carbon steel, has excellent resistance to thermal shock, can be used to repair TSA field joints, can be used on SA2.5, SP11, SP3, ST2, UHPWJ surface pretreatments, can be applied to hot steel up to 150 degrees Celsius, and can be used at cryogenic temperatures down to -196 degrees Celsius. And to re-summarize the product range again, for planned maintenance shutdowns and regular maintenance for process piping and equipment operating below 230 degrees Celsius, Interbond 2340 UPC should be used. For planned maintenance shutdowns and regular maintenance for process piping and equipment where operating temperatures are cyclic and are between 230 degrees Celsius and 400 degrees Celsius, Intertherm 751 CSA should be used. And for applications to hot process piping and equipment operating between 60 degrees Celsius and 230 degrees Celsius, Intertherm 2205 is the product of choice. Thank you for listening to this presentation.